Welcome all. So, today we will start the lecture for this week. We will start with the analysis of the loading on the structure caused by the external air blast. So, last time what we saw was we saw above ground structure subjected to blast loading and they had no openings. Okay. So, today we will be dealing with rectangular structures with openings. So, last time we started with assumptions. Okay. Our structure was rectangular, that was the first assumption. Okay. The structure was above ground, that was the second assumption. First was rectangular, second was it is an above ground structure. Okay. And the blast wave is acting such that the structure is seeing a planar wave front. Okay. So, these are the three key assumptions that we had. Okay. After that we saw how to calculate the effect of the blast loading on the front wall, how to calculate the effect of the blast loading on the side walls, on the roof, and finally on the back wall. Okay. So, what we did? We started with our blast load. Okay. First what we need to do is that we need to see what type of explosives we are having. Okay. So, the weight of the charge, okay, depending upon whether it is a TNT, it is actually made of TNT or some other explosives, we convert it into equivalent TNT. Okay. So, if it is TNT, then we just multiply it by 1. If it is made of some other materials, then due to the uncertainty, we multiply it by 1.2, that is an increase in 20%. Okay. So, this is the characterization of the explosives. Okay. After the explosive is being characterized, we will look into where the blast is occurring. Okay. The blast is occurring on the surface, if it is occurring on the air, or if it is occurring on the top. Okay. So, depending upon the case, we can consider it as a free air blast, or surface burst. Okay. So, after that we categorize the type of blast that is occurring. Okay. Once we have done this too, then what we do is that we take charts from TM5 1300 or UFC 3340 and then calculate the parameters. Okay. So, in order to calculate the parameters, first we need to calculate the parameter Z. Okay. Z is nothing but standoff distance divided by the cubic root of the weight. So, weight we get from this chart and standoff distance we calculate from where the point of interest is from the explosion. Okay. So, this will be the R, okay, depending upon what type of blast is occurring. Okay. So, we get the R, we get the W, and then we calculate the Z from there. Okay. Then what we do is that we take TM5 1300 or UFC 3340 and on the x axis we have the value of Z. Okay. And on the y axis we have the other quantities such as overpressure, incidence pressure, reflected pressure, positive duration of the impulse, negative duration of the impulse, positive blast wavelength, negative blast wavelength, okay, positive time phase, okay, negative time phase. Okay. So, all these quantities are denoted by graphs. Okay. And these graphs are specific to the type of blast, okay, that we have already characterized. Okay. So, depending upon the type of blast we get different graphs, okay, and we take the appropriate graph, we go in the x axis, and from the x axis we calculate the quantities of interest. Okay. Once we have the quantities of interest, what we do is that we then construct the actual incident curve. Okay. We calculate the actual incident curve. Okay. Basically we make this curve. Okay. So, this is called the Friedlander's profile. Okay. So, PSO, T positive, T negative, and so on and so forth. Okay. So, once we have this thing, then depending upon on what phase we are calculating. Okay. Let us say we are calculating on the front face. Okay. For the front face we convert the actual loading in an equivalent loading. Okay. So, for that what we do is that we preserve the total impulse. Okay. So, in this case the positive impulse will be area under this curve. Okay. Area under this curve. Okay. Then we represent this thing by a triangular loading. Okay. Represent this thing by a triangular loading. We keep the y axis, the pressure same, and we calculate the equivalent positive phase duration. Okay. Similarly, we do for the negative phase. and then we construct a equivalent pressure curve. Okay. There will be a lag between the positive and the equivalent positive and the equivalent negative curve, okay, due to the matching in this area. Okay. And this is the loading, this is the pressure that we apply on our frontal face. Okay. And similarly, we calculate the equivalent curves for our side face, our roof and the back face. Okay. And using this equivalent loading, we then calculate the total force acting on this surface. Okay. So, this is the procedure that we were following for a rectangular structure, okay, that was subjected to a blast loading and it was located above and it had no openings. Okay. So, today we will be dealing with the same type of structures. The structure is again rectangular. Okay. Today also the structure will be rectangular. It will be above ground. It will be subject to a blast loading having planar wave front. Okay. Only difference is that today there will be openings. Okay. There will be different vents and different types of openings. Okay. So, last time we dealt with structure having no openings. Today we will deal with the structure having openings. Okay. So, that will cover our total envelope. Okay. So, we will see how this thing is been taken into account. Okay. So, general overview of the structures with opening. Okay. So, two main structural configurations regarding exterior openings are there. Openings that are present in forms of windows, doors in front, rear and side walls. Okay. Meaning the exit type of openings. Okay. Front wall, okay, side walls or rear walls. Okay. Then the other type is that the opening is only in the front wall, other walls are without openings. Okay. So, in one case there will be opening in all the walls, okay, and in the other case there will be opening only in the frontal case. Okay. So, there will be opening here only. Okay. So, these are the two main structural configurations that we will be dealing with. Okay. The second configuration is the most common due to the interior partitions restricting blast wave flow inside. Okay. So, the most common is the second type of configuration where we have opening only in the frontal zone. Okay. So, interior blast load increase due to the reflection of interior components. Okay. As we have seen, due to the reflections, okay, the intensity of the blast loading will be augmented out here. Okay. So, the main focus of this section is on the blast loading on the structure with openings primarily on the front face. Okay. So, since this is the most common case, we will be mostly focusing on the structures having frontal openings. Okay. Okay. So, moving ahead. So, what are the effects of opening on blast load? When the shock front hits the front wall, okay, your shock front is coming and it hits the frontal wall. Okay. The frontal wall sees the shock front. Okay. Instantly the incident pressure is amplified. Okay. Due to the reflection, the incident pressure is amplified. Okay. Windows and doors almost fail immediately. Okay. Unless specifically designed. Okay. If we have windows and doors, okay, that are seeing this type of blast load, they will fail instantly unless and until they are designed for this purpose. Okay. Even if we design the doors, okay, and the windows, okay, so what we will do if we are doing a frontal design, okay, and if the blast pressure is traveling like this and this is hitting my doors or the windows, okay, what is going to happen? A tremendous amount of pressure is going to be applied on this structure. So, if we can make our system thick enough, okay, or resistant enough so that it can take the loading of the blast load, still there will be a portion lacking here where the joints are there. Okay. So, joints are the most critical component when we are dealing with any sort of openings. Okay. When we are dealing with doors, when we are dealing with windows, not only the configuration of this plate, okay, from which the door or the window is made of, the configuration of the joints are very critical. Why? Because in a very small area, okay, the cross sectional area of the joints, okay, whether they are acting in shear, whether they are acting in bearing, will be very small. So, in that small cross sectional area, the entire thrust of the blast load transmitted to the window or the door has to be sustained. Okay. So, most of the time what it is seen is there, though the structure is designed, okay, the front face is designed, the doors, windows, everything are designed, most of the time the failure occurs into the excessive distortion of the joints. Okay. The joints will excessively distort, like if it is designed like this, it will distort excessively like this. Okay. And at the end of the day, the doors, okay, the frontal doors or the windows are not going to function. Okay. So, after a particular blast loading, if it is having a sufficiently high intensity, this mechanism will be not working. Okay. It will be jammed and the functioning of the door is lost. Okay. So, in this type of cases, the proper design of the joint is also a paramount concern. Okay. So, after that what happens? The blast pressure then flows through openings into the structure. Okay. If the doors and windows are not designed to take care of the blast load, the blast loading will be flowing inside the structure through this distorted openings. Okay. That will generate internal shock fronts. Okay. So, imagine a high intensity blast is there, okay, and it is entering this closed box. Okay. So, it will instantly generate a internal shock front. Okay. So, after that the individual internal fronts will combine and expand throughout the interior. Okay. They will be acting throughout the interior. Okay. The interior pressure is weaker than exterior incident pressure, but strengthened due to the internal reflections. Okay. Since this is a case of internal reflections, the augmentation in the pressure intensity will take place instantly. Okay. So, if it was a free air blast or a surface type of blast, okay, with only a frontal panel, then it can be taken care of. But since it goes inside a closed box, okay, due to the massive reflections, okay, the intensity increases manifold. Okay. So, here we will see the an idealized structure and the pressure flow that is occurring inside it. Okay. So, let us say we have a opening on the front wall. Okay. So, this is the opening, okay, and it has a, this thing is shown in plan. So, the cross sectional area is, let us say, A0. Okay. Okay. So, total opening of the front area are combined into a single fictitious opening at the center. Okay. So, there can be multiple openings. Okay. So, what we are saying is that we are taking the area of all the openings and combining them together. Okay. A real structure might look like this, okay, with door and windows opening. What we are doing is that we are making an equivalent structure that has a sum total of an equivalent area, that is the sum total of these three areas, area 1, area 2, area 3. So, sum total of area equals to A0, okay, that is represented here. Okay. So, the blast pressure enters through the opening and it loads the interior surface. Okay. It loads the side wall, frontal wall, back wall. Okay. So, here also we can see the blast load is entering through it and it is loading the entire structure. Okay. So, it travels from front wall interior surface to side walls and roof interiors, and then it finally reaches the back wall interior surface. Okay. So, this is how it is flowing. Okay. Okay. So, here we have the geometry of the, this is the section of the box type of structure with opening A0, and this is the plan of the structure. Okay. So, basically it is a box with height h and cross sectional dimensions L cross W. Okay. So, after that we have a idealized structure and pressure flow. Okay. Then we will try to idealize the pressure flow. So, the pressure time load curves for these surfaces are idealized. Okay. So, what after that what we are doing is that we are presenting the idealized pressure time curve. Okay. So, for the different wall surface, for interior front wall surface, for interior side wall or roof surface, and for the interior back wall surface, we are presenting the idealized curve. Okay. Here we can see the difference here. Okay. The first it reaches the interior front wall, after it reaches the interior side wall, and after that it reaches the interior back wall. Okay. So, we can see there is a lag in the time out here. Okay. So, the exterior blast pressure on non-frontal walls are unaffected by opening and are then calculated as usual. Okay. So, the non-frontal wall, whatever is the pressure on the non-frontal wall, they are unaffected by the openings and then they are calculated as usual. Okay. So, what we are trying to say is that since the pressure has entered here, okay, there is a difference between the interior pressure and the exterior pressure. Okay. Earlier what we were dealing is that since there was no opening, there was only the exterior pressure acting. Okay. And on the non-frontal walls, okay, the exterior pressure, okay, remains the same as before. Okay. So, exterior pressure remains the same, interior pressure we are calculating using this nomenclature, okay, using this idealization. Okay. So, we have to combine whatever we have learnt in the last time. Okay. We have to calculate the internal pressure also, we have to calculate the external pressure, okay, and the total effect of these two things on the structure has to be evaluated in order to design so that it resists the blast loading properly. Moving ahead. So, the purpose and the design implications that we learned. Okay. Our main goal is to determine the interior blast load on exterior walls to predict maximum outward wall motion. Okay. So, this is our main goal. Okay. We have to determine the interior blast loads, okay, on the exterior walls to predict the maximum outward wall motion. Okay. See what is going to happen out here. If this is flowing like this, okay, there will be an internal pressure, okay, and on this exterior wall it is going to push it outwards. Okay. So, it is trying to do like this. Okay. So, we have to calculate this effect, okay, the maximum outward wall motion. Okay. This motion we will have to calculate. Okay. The interior loads should not reduce exterior positive phase loads. Okay. So, we have earlier seen that we are able to calculate the exterior positive phase loads. Okay. So, it should not be taken as a compensatory action. Okay. So, it should not reduce the external positive phasing load. Okay. It should not be taken as a compensating for each other. Okay. Why? Because phasing between interior and exterior load is uncertain. Okay. Okay. See, this is different from static cases. Okay. In static cases, we can say that one exterior loading is acting like this, interior loading is acting like this. Okay. And they can have a reducing effect. Okay. But here we have seen that the time at which the interior loading is acting and the time at which the exterior loading is acting is highly uncertain. Okay. So, there is a high chance that they are not going to cancel out or reduce the effect. Okay. So, that is why this thing is not allowed in the analysis. Okay. We cannot reduce the effect of the interior effect of the equivalent or the final load, taking into account the difference between the interior and the exterior loading. Okay. So, normally what happens is that the interior loads lag exterior positive phase. Okay. So, the interior load is coming behind the exterior positive phase. Okay. So, the interior phase might be doing this, but once the effect has subsidized, the exterior loading might be doing this, and once this effect has subsidized, the interior load might do like this. Okay. But they are not occurring at the same time. So, hence their effect cannot be taken as to be reducing due to each another. Okay. So, we should not reduce the exterior effect of the exterior loading. Okay. The interior load duration is longer due to reflections. Okay. Since this is a closed surface, there will be reflections occurring, and the interior, therefore, the interior load duration will be longer than the exterior load duration. Okay. So, what we need to do for the design? For the design, we combine the interior blast load with the exterior negative phase loading. Okay. So, we take an additive approach. Okay. We are not going to reduce the effect of the interior positive phase with the exterior positive phase, that we are not going to do. What we do is that we take the interior positive phase and augment this thing with the exterior negative phase, okay, to assess the maximum outward motion. Okay. So, this is the worst case scenario. Okay. So, we need to understand this. Okay. So, a blast loading is acting. Okay. Since there were, let us say there are two cases. Okay. no opening, opening. Okay. So, in no opening case, as we have seen earlier, the blast load will be acting on the frontal face, they will be acting on the side faces, roofs and external walls. Okay. So, what they will do is that they will try to do a motion like this, okay, internal squeezing motion, okay, the positive phase. Okay. After that, there will be a negative phase where the suction will occur, and this is going to go in the behave in the outward direction, though the magnitude might be less, but there will be a positive phase and there will be a negative phase. Okay. This is due to the effect of the loading on the exterior wall, which is same for both the cases, with opening, without opening, the effect on the exterior wall is same. In addition to this, there is a opening out here. Okay. So, what will happen is that due to this opening, okay, this structure is going to try to bulge out like this. Okay. So, once it tries to bulge out, okay, so there is a bulging out effect due to the positive interior loading pressure, and there is a bulging in effect due to the positive exterior loading thing. Okay. So, since they are trying to cancel each other, we should not take them together. Why? Because they are not going to act at the same time. Okay. Phasing is uncertain, so they might not act at the same time. Okay. In order to assess the worst possible condition, what we take as positive internal pressure, that is trying to bulge it outward, and negative external pressure, okay, that is also trying to move it outwards due to the suction effect or the negative effect. Okay. So, these two we combine, and combining these two we assess the maximum outward motion, okay, that is the worst case scenario. Okay. Use the exterior positive phase loading is used alone to determine the maximum inward positive response. Okay. So, one response is positive outward, okay, due to the internal, plus positive outward due to the negative external. Okay. Other case is that in order to assess the maximum inward, we take the positive external. Okay. So, these are the two worst cases that we take. Okay. So, positive external to assess the maximum inward positive response. So, this is positive external, and here we do negative external plus positive internal to assess the maximum outward. Okay. So, this is for the inward motion and this is for the outward motion. Okay. So, this is how we combine them together. So, interior partitions and opening. Interior partitions usually required, they are usually required to resist blast pressure that leaks inside. Okay. So, some sort of partitions are required in order to resist the leaking of the blast pressure inside. Interior partitions parallel to the front wall behave as back walls. Okay. So, if this is the front wall and there is a partition parallel to this wall, then this will behave as a back wall. Okay. So, it will reduce the effective length of the side walls. Okay. Interior partitions perpendicular to the front wall acts like a side wall. Okay. So, if this is the side wall and if it is perpendicular, there is an interior partition wall, then it will act as a pseudo side wall. Okay. So, what it will do is that it will reduce the effective length of the front wall. Okay. So, we are looking this thing geometrically. Okay. So, openings considered only between internal partitions act as vent opening. Okay. So, if there is an internal partitions, okay, and there is an opening between the internal partitions only, then they are considered as a vent opening. Okay. The orientation of the shock front. Okay. So, some procedures are developed assuming shock front strikes front wall head on. Okay. It means that the shock front is hitting the entirely the front wall. Okay. This results in the most severe internal shock effect. Okay. So, this creates the most worst case scenario. Okay. So, use of this procedure for oblique shock front angles yield conservative estimates of interior blast. Okay. So, what we are saying is that whatever might be the case, we are always assuming, if we are looking into a plan, we are assuming that the shock front hits the front wall fully. Okay, it is not at any angle. Okay, it might be a case where the shock front is acting at an angle, as we have seen earlier. Okay, if this is the angle of attack. Okay, but for the worst case scenario in the design sense, we always assume that it is acting head on. Okay, so this will give us a conservative effect, when in reality if the shock front is supposed to hit at an angle. Okay, so we will be over safe in our design. Moving ahead. So, front wall with openings. Okay. So, clearing time for reflected pressure on the front wall with openings. Okay. So, what happens with the reflected pressure? The reflected pressure clearing time depends on the time for refraction waves to sweep the wall. Okay. So, the clearing time, okay, it will depend upon the time, okay, till the entire wall is being affected. Okay. So, for walls with openings, clearing occurs around both edges of opening and edge of the wall. Okay. So, the clearing effect will be here and the clearing effect will be on the edges of the opening also. Okay. Clear time may be significantly reduced compared to a solid wall due to openings. Okay. Since there are openings there, okay, the total time required to the wave to move past this surface, okay, is reduced, okay, because it has got an access point, okay, to travel through this thing. Okay. So, as compared to a proper solid wall, the clearing time is normally less. Okay. So, the pressure time relationship of blast load on front wall with opening remains the same as for solid wall, but clearing time is shortened. The pressure time relationship is same, but the time required to the blast to travel through this thing is less. Okay. If window or door covers, okay, like we talked about the frangible element do not fail immediately, clearing time should not be reduced. Okay. So, if there are frangible elements, okay, that is the elements which will fail, okay, or which will be dismantled as soon as the blast load reaches a certain preset peak value. Okay. Then all the things that behave as a opening. Okay. Let us say we have a wall. Okay. Okay. So, in normal cases this is behaving, there is an actual opening, okay, and this is behaving as a frangible element. Okay. Normal operation condition, this will behave as a solid wall, and during a blast loading, okay, if a blast loading occurs and if it reaches a certain peak value, peak critical value, then this thing becomes dismantled. Okay. There is a opening is created. Okay. So, if this is going to happen, then clearing time can be reduced. Okay. But if the frangible element are not failing instantly, then the clearing time should not be reduced. Okay. Because what will happen is that the pressure will not get this path to traverse through the system. Okay. So, now we will see the weighted average clearing distance. Okay. We will try to calculate the weighted average clearing distance. Okay. So, to evaluate the reduced clearing time, we have introduced weighted average clearing distance. Okay. Okay. So, what we do is that there is a subdivision of the typical wall with openings. Okay. So, the front wall is divided into rectangular areas based on opening locations and dimensions. Each area is classified by a number and the location of clearing sites with assigned clearing factor for delta n. Okay. So, let us say we are looking into area 1. Okay. So, for that delta n is 1, and what it has 2 adjacent clearing sites. Okay. So, if you look here, the 2 adjacent sites have a clearing site. Okay. Area 2, okay, the 2 opposite sides have clearing sites. Okay. 2. Okay. So, 2 opposite sides. Okay. Here adjacent sides. Okay. 2 again opposite sides, 2 again opposite sides. Okay. Then there will be one more 2 out here, 2 opposite sides. Okay. Then delta n is taken as 0.5, 3 one side. Okay. So, 3, if you look into 3, there is only one opening side, 3 one opening side, this is opening. Okay. So, this were the openings. Okay. So, again 3 one opening side. Okay. and 4 if it has no opening sides. Okay. If you look here, it is locked and it has no opening sides. Okay. So, depending upon the relative location, we assign delta n value. Okay. So, the clearing distance h for each area is determined as area 1 for smaller of the width or height of the area, area 2 distance between the opposite clearing sides, and area 3 distance between the clearing sides and the opposite sides. Okay. So, now we are trying to assess the distribution of the pressure on the walls. Okay. So, today we will stop here, we will continue from the next time. Thank you.